Hello, everybody. My name is JenFarner, and I'm here to present my presentation on the Forsyth Fire. So I appreciate everyone attending, and my presentation is titled Echoes of Fire of Geospatial Analysis of the Forsyth Fire in 2025 in Pine Valley, Utah. Today, I'll walk through how the landscape, its slopes, winds, and history of past burns controlled the movement and the intensity of the Forsyth Fire earlier this summer. This diagram illustrates the basic contents of the Forsyth Fire and the forces that shaped its very rapid movement into Pine Valley. A lightning strike that occurred approximately 9 days earlier had sparked the fire. It smoldered in a tree near the ridge until it became visible about 5:30 p.m. on June 19th. The winds picked up to nearly 20 miles per hour, blowing downslope through Forsyth Canyon, putting Pine Valley directly in the fire's path. The fire dropped quickly through the canyon, covering roughly 3.5 miles in just about 14 hours. The path crossed the Saddle Fire reburn area with lower severity, but steep canyon walls and continuous fuels increased the fire's spread. This simple cross-section sets the stage for the analysis that follows by showing the key interacting factors: wind direction, terrain slope, fuel continuity, and the timing of the ignition. I will now introduce the objectives that guided the entire workflow, from the satellite image processing to the final modeled spread trajectory. I quantified vegetation vigor, canopy moisture, and burn severity using these 5 indices derived from pre- and post-fire Landsat 8 imagery. I evaluated the alignment between observed fire spread corrections and the dominant wind direction to test for wind channeling through Forsyth Canyon. I compared burn severity across 4 legacy fire zones to understand whether past fires moderated or amplified severity. I examined how slope, aspect, and solar exposure influence both moisture loss and fire intensity. I integrated these components to understand how terrain, wind, and disturbance history shaped the Forsyth Fire rapid movement in its first 14 hours. This workflow shows how I analyzed the Forsyth Fire. I started with the hypothesis linking terrain, wind, and legacy fires. I then gathered Landsat imagery, digital elevation models, fire perimeters, and wind data. I derived spectral indices and determined severity. I calculated slope and aspect of the terrain, built legacy fire zones, and mapped the severity clusters with local RANS-I. I compared the spread direction with wind data for remote weather stations. I combined these results to explain how wind alignment and fuel shaped the fire and why it aggressively followed Forsyth Canyon. Finally, I developed a coherent explanation of how terrain, wind, and legacy burns shaped the Forsyth Fire after the initial 14-hour run down Forsyth Canyon. Let's dive into each step of this fascinating study. This map shows the whole study area and the core data sets used throughout the analysis. I combined the Forsyth Fire perimeter with the 2 legacy fire scars, the 2016 Saddle Fire and the 2018 West Valley Fire, to understand how past burns shape fuel patterns. I also included the Pine Valley community boundary and the Forsyth Canyon terrain outline to define the physical structure of the study site. Bringing these data sets together provided the geographic foundation for analyzing how terrain, wind, and legacy burns influence the Forsyth Fire path. In this phase of the study, I calculated several spectral indices to measure how vegetation and fuels changed before and after the fire. NDVI and NDMI were computed for both pre-fire and post-fire imagery. And the differences, delta NDVI and delta NDMI, capture shifts in vegetation vigor and canopy moisture. The NBR was generated, and those values were used to compute the NBR, which is a direct measure of burn severity. And because vegetation density varies across the landscape, I then standardized DNBR into RDNBR, which adjusts for pre-fire conditions and allows for more comparable severity estimates across the fire area. Finally, I applied the MTVS severity classes to categorize the landscape into low, moderate, and high severity. Together, these indices provided a consistent quantitative way to assess how the Forsyth fires altered vegetation structure, moisture, and overall severity. The severity results reveal an evident spatial pattern. In the DNBR and RDNBR maps, the highest burn severity is concentrated in the lower portions of the canyons. These areas form the highest topographic funnels, and both burn indices consistently classified them as low to moderate or moderately high severity. In contrast, the north-facing slopes show noticeably less moisture loss, consistent with their cooler, shaded microclimate and typically higher pre-fire fuel moisture. The change detection indices reinforce this interpretation. Delta NDVI and Delta MDMI show significant vegetation and moisture loss throughout Forsyth Canyon interior, with the steepest declines occurring in those same lower sections where fuels were continuous and winds were aligned with the slope. The correlation heat map supports these relationships. Pre-fire vegetation greenness and moisture remain strongly correlated, indicating that greener areas were also more hydrated before the fire. However, both indices show only weak correlations with DNVR and very weak correlations with RDNVR. This indicates that pre-fire vegetation alone did not drive burn severity in Forsyth Canyon. Another strong relationship in the matrix is the correlation between DNVR and RDNVR. Both metrics highlight the same high severity zones, showing that terrain and fire behavior, not pre-fire vegetation, controlled severity, concluding that north-facing slopes stayed more hydrated and burned less. Terrain structure is a main driver in the canyon-dominated fire behavior. In this part of the analysis, I derived several key terrain metrics from the 10-meter digital elevation model to understand how landscape shaped fire behavior. First, the slope was calculated to identify terrain steepness, which matters because fire spreads faster on steep slopes where flames tilt toward unburned fuels that are mainly ground cover. Secondly, aspect was calculated to represent the direction each slope faces, measured clockwise from north. I then converted aspect into southness index, producing a -1 to +1 scale, where positive values indicate sun-exposed, south-facing slopes that dry out faster and are more prone to burning. Finally, I grouped these slopes into 4 classes, defined by degrees to compare severity across terrain types. These metrics help explain why some areas burn more intensely. This map shows the combined slope and aspect results, and there is a clear relationship between terrain and burn severity. Steeper south-facing slopes saw the most intense burn patterns. The highest severity occurred on slopes between 18 to 23 degrees and on slopes steeper than 25 degrees. These steeper slopes promoted faster upslope and downslope fire movement, allowing flames to preheat vegetation and accelerate spread. Aspect was also key. The sun-exposed south-facing slopes burned hotter, while shaded north-facing slopes retained moisture and burned less. Valley bottoms between the canyons, where cold air drainage and higher humidity tended to show moderate behavior and had noticeably lower severity levels. Altogether, these topographic patterns show that fire intensity in Forsyth Canyon was driven far more by slope and solar exposure than by pre-fire vegetation, consistent with the correlation results. I divided the Forsyth landscape into 4 legacy fire influence zones to evaluate how past burns affected severity. These zones follow established distances used in prior fire effects research and provide a consistent way to compare fuel conditions across the fire area. The reburn zone, areas that burned in both legacy fires and the Forsyth fire. Ring zones, interior portions of the legacy scars with 6 to 9 years of regrowth. The edge zone, transitional fuels along the legacy boundaries where edge effects are more intense. And the control zone, mature, undisturbed forest outside legacy influence used as a severity baseline. This slide illustrates how the Saddle and West Valley legacy scars influence the Forsyth severity with noticeably different patterns on each side of the Forsyth perimeter. The Saddle reburn zone had higher severity due to denser fuels from older regrowth, while the younger vegetation in the West Valley reburn zone resulted in lower severity. The Saddle Edge zone experienced the highest severity with a sharp transition from mature regrowth to unburned forest, creating a strong fuel gradient. In contrast, the West Valley Edge had only light to moderate severity due to younger, lighter fuels. In the Saddle Ring zone, regrowth produced a continuous mid-height fuels, leading to elevated severity. In contrast, the West Valley Ring zone had less developed fuels and consistently lower. The control areas, unaffected by any legacy fire, showed intermediate severity. In summary, the highest severity of the Forsyth fire was found in areas with older legacy regrowth and dense fuels, particularly along the saddle edges, while younger West Valley scars had lower fire intensity. This highlights how the time since the last burn and fuel transitions affected the fire's behavior. In this phase, I used local Moran's eye to analyze burn severity clusters across the Forsyth fire footprint. This method evaluates each location relative to its neighbors to identify significant clusters of high or low values, yielding 4 key cluster types. The high clusters in red indicate areas with high DNVR values surrounded by similar severity, primarily located in the lower and central Forsyth Canyon and at canyon mouths. corresponding to steep terrain and main fire runs. The low clusters in dark blue indicate areas of consistently low severity, often found along the top ridge and shaded north-facing slopes, which retain more moisture and burn less intensely. The pink and light blue, high-low, and low-high outliers indicate transitional zones with abrupt severity changes, often due to localized fuel or microclimate differences. The results show that burn severity wasn't random. High-severity clusters consistently formed in the lower canyons, with clear transitions from low to high intensity. Local Moran's eye revealed the spatial structure behind these patterns, continuously high-severity corridors, sharp changes in intensity, and sheltered pockets shaped by terrain and fuels. This spatial context was crucial for interpreting the fire movement in Forsyth Canyon, confirming that topography was a major driver of where most severe burning occurred. Now that the terrain had been analyzed, I introduced the meteorological data from the Pine Valley remote weather stations to assess how winds shaped the fire's movement. During the first 14 hours after ignition, the winds were consistently aligned around 28 to 30 degrees, pointing directly down Forsyth Canyon. Using that dominant wind angle, I built a windrows, classified slopes as windward or leeward, calculated fire spread azimuths from perimeter changes. I then compared those to spread directions with the wind to create an alignment metric named align diff, which measures how closely the fire's movement matched the wind. Finally, I correlated the line diff with RDNVR to see whether more substantial wind alignment corresponded to higher burn severity and whether lower alignment reduced that effect. This slide combined with wind exposure and alignment results to show how closely the Forsyth fire followed the prevailing winds during its first 14 hours. Using the wind direction of about 28 degrees, I classified slopes as windward in blue, meaning they faced directly into the flow, and leeward in pink, meaning they were sheltered from it. When these are overlaid with the DNVR map, the windward slopes lined up almost precisely with the higher burn severity, while leeward slopes showed much more lower intensity. This indicates that wind alignment strongly amplified fire behavior. The directional alignment map reinforces this pattern. Each pixel is labeled as aligned, near aligned, crosswind, or opposing, based on how closely its spread direction matched the prevailing wind. This is quantified using the align diff metric, where lower values indicated strong wind spread coupling. Align diff correlated with RDNVR at negative 0.68, showing that better alignment produced a higher burn severity. The alignment classes on the top of this map reflect clearly. The red zones, strongly aligned, match the high severity corridors in the lower canyons, while the orange and yellow zones marked weaker coupling and lower severity along the southern ridge. The blue triangle highlighted the fire's east-northeast elongation from the ignition point down toward Pine Valley. Most spread directions fell within about 30 degrees of the prevailing wind. The rose diagram on the right clearly shows that Forsyth fire was strongly wind-driven, with a tight clustering around the 27 to 30 degree wind axis. Together, the windward-leeward map, alignment classification, and rose diagram tell the same story. The Forsyth fire spread fastest and burned more intensely where the wind direction, slope orientation, and canyon shape were aligned. This slide provides the comprehensive analysis of how terrain, wind, and fuel conditions collectively contributed to the Forsyth fire's swift 14-hour movement from the ridge onto the valley. Forsyth Canyon provided a direct pathway for spread. Its steep south-facing slopes with drier ground vegetation and downslope orientation created a natural conduit for the fast fire movement. The fire spread direction closely matched the wind direction about 27 to 30 degrees, and that tight wind spread alignment, shown in the live diff results, intensified the heating and accelerated the forward run. Fuel continuity added another layer of influence. Along the older saddle fire scar, regrowth in the edge and ring zone supported the high-intensity burning. In comparison, the younger West Valley scar had lighter fuels that reduced severity and helped limit the eastward spread. Reburn patches within both scars showed the most moderate severity. Overall, the severity maps and cluster patterns, especially in the high corridors in the lower canyon, mirror the same downslope pathway, reinforcing how terrain shape, wind alignment, and fuel structure work together to drive the fire's progression. Ultimately, this analysis shows that several key geographic and environmental factors also contributed to the continued fired behavior after the Forsyth Canyon run. Each canyon shape played a central role each time the fire moved downslope as it progressed along the rim. The terrain, slope orientations, and the direct connection to the ridgeline created the official natural corridor for the fast downslope spread. The prevailing winds aligned with the canyon axes, accelerating the fire's downhill movement as the fire spread east from the ignition point. Its advance slowed due to the misalignment with the wind. Fuel patterns added yet another layer of influence. Mature, continuous fuels in the lower canyons enabled the fire to build significant intensity. The legacy burn scars influenced fire severity, reducing intensity in some interior reburn areas and restricting fire movement. Specifically, the West Valley fire scar slowed the fire's eastward spread by limiting fuel availability. The spectral and spatial analysis bring these factors together, showing once again the highest burn severity consistently occurred where terrain, wind alignment, and fuel continuity overlapped. This study is not only about the behavior of the wildfire, it's about the community that rose in its aftermath. The force of fire did not descend into Pine Valley by accident. It followed the shape of the canyon, the push of the wind, and the fuels that had slowly returned over the years. By studying how these forces intertwined, we gain clarity that strengthens preparedness, improves mitigation, and supports wiser decisions for the future. And we honor the families who watched the fire move from the ridge into the valley and experience that still echoes across the landscape today. Pine Valley is defined not just by fire, but by resilience, by a community that, like the phoenix, rises from the ashes stronger and more determined than before. My hope is that this work continues on and in some small way protects that resilience as it continues to grow. Thank you for attending my presentation, and with that, I'm happy to take any questions.